Berends from the Netherlands, and I'm to talk about rapid and reproducible resistance analysis for all using the AMR Package For R. I have no conflicts of interest to declare. So I wanted to start with a short introduction to our work field. So we're from the University of Groningen, and as medical researchers we are also working at the University Medical Center, and we focus on epidemiological and data scientific research on new methods. It's important to introduce some bits of medical microbiology as well. So, for you all to understand, of course, people get infectious diseases, killing millions per year. In the USA alone, I looked it up, it's around 160,000 people a year. Many of those infectious diseases are caused by bacteria. Luckily, bacteria can be killed or inhibited in growth by antibiotics. But as you all know, bacteria are smarter than we like, and they can become resistant. So bacteria are also quite on their own. They differ in both prevalence, so the kind of bacteria occurring in different places in the world, and also differ in resistance between countries and between continents and states, and maybe even more detailed geographic regions. So that's also important to know, because doctors who treat patients for those reasons seldomly know which bacteria are causing infections unless laboratory tests are done, and they also seldomly know exactly which antibiotics would work well on the specific bacteria causing the disease, unless again laboratory tests are done. So how can we help doctors treat patients without knowing this? Well, they should ask their epidemiologist or data scientist and let them watch this presentation. Another important thing is taxonomy. I think most of you will know taxonomy. Here's an example of the different taxonomics levels, so from kingdom to species. There's also some in between, but these are the most important ones for now. And here you see an example for humans, right? We are Homo sapiens, genus Homo, and we all go down to the kingdom of Animalia. If we look at E. coli, for example, a bacterium, then you see it's part of the kingdom of bacteria, obviously, and here's all different levels until we get to the genus level for Escherichia and the species level coli. Taxonomy is important because we needed to limit development of resistance. The goal for doctors to treat antibiotically is always to treat as specific as possible. Because some antibiotics work here, they are broad spectrum, which is actually the worst choice, but sometimes you don't have choice, right? But some antibiotics work here, that's already better, and some work here, that would be the best choice. So how do you know which antibiotics to give if you don't know the bacteria, or maybe do know the bacteria, but you want to know it on a general level for your ward, or for your hospital, or for your region. So what must they have or know? And with they I mean those people analyzing your data scientists or epidemiologists. Well, they should have good questions, and they should be asked by other doctors perhaps, like which drugs would work well in my hospital for treating E. coli, or which drugs would work well in my hospital if I don't know the bacterial name. They should, of course, also understand something about epidemiological dependencies and methods, like how should I define a patient's episode, right? If you get a urine tract infection in February and you get one in October again, then that's two different episodes, and you should treat it as two different patient episodes. They should also be able to select bacterial isolates that are suitable for analysis. For example, if I am treated for a bacterial infection in my blood, I have a systemic infection, and my blood gets drawn 5 times a week, then I would have the same 5 isolates on the laboratory and results of it in my laboratory data. And you would absolutely want to correct for that, because you don't want to have duplicates in your data. It's hard to unduplicate. So how do you do that? And you need to have reliable reference data to be able to answer questions like which antibiotic are glycopeptides. It's a group of antibiotics. Sometimes important, if somebody asks, I would like to know how glycopeptides work, or what the success rate is if I would treat with that. You should be able to answer it. And you should also have details about microbial taxonomy, as I showed you. If you don't know the order or the family or the genus of the species you have, then it's hard to stratify based on those data. And guidelines, of course, for determining and analyzing antimicrobial resistance. There are guidelines available, but there's no software that's able to apply this, or at least there wasn't. So here we present AMR, the AMR Package for R. It enables standardized and absolutely reproducible antimicrobial resistance analyses, and it enables application of evidence-based methods for cleaning and analyzing data from laboratories and hospitals. You can also use it to integrate it into existing international workflows like those by the WHO or EARSnet, which stands for European Antimicrobial Resistance Surveillance Network, and it's completely independent of any laboratory information system. Besides that, it's of course free and open source. It's up to date and long-term maintained for the microbial taxonomy and the guidelines. We keep track of that. It's also independent of any other R package. It does not import any other R package, although it works very well with the tidyverse. I'll get to that. And it's stable and fast. So we included information about bugs, taxonomic data from the Catalogue of Life, which is a very authoritative source for taxonomy, and we included every detail of the taxonomy from kingdom to subspecies, including gram stain. We also included information about drugs, pharmaceutical data like ATC codes, official names, official groups, and antibiotics, antimycotics, and antivirals. So antimycotics are for treatment against fungi, and we also included 5,000 brand names and DDDs, which stands for Defined Daily Dose. And we taught the package to understand laboratory output and methods. If you work in infectious diseases, this really makes sense, but I think I'll skip it now. We're very happy that it's been downloaded over 35,000 times already since the first release 2 years ago, which is from CRAN logs, this data, and this consequently is a underestimation because it only tracks one repository, albeit a very popular one. And it's been downloaded from 112 countries already, and we are especially fond of the fact that it's being used in HIPCs, a lot of them. So there's a list of heavily indebted poor countries, and those countries do not have a lot of resources. You know, some organizations in those countries might not even be able to afford SPSS or other statistical software, but they can afford R, and they can afford our R package because, of course, it's free. And we're very happy that antimicrobial resistance analysis can now be done in any country in the world. So what can it do? Well, you can use it to coerce raw, unclean data that you get from laboratory or hospital systems. Here's an example. You see here the official name of glucoxacillin, which is an antibiotic, some derivation from other countries, other languages, and a brand name. And brand names differ per country as well. Official codes, one by EARSnet, by the WHO. This is the ATC code used in pharmaceutical systems, also by the WHO. And this is an ID, a compound ID by PubChem. There's of course always arbitrary codes you find in systems, laboratory systems, and as a proof of principle we added some incorrect spelling. So what you can do with our package is just coerce all this to FLC, which is the abbreviation we took from EARSnet as the abbreviation for this antibiotic. And with bacteria exactly the same thing. There's a Staphylococcus aureus, a bacteria, and there's of course known abbreviations and also other codes people think of and have it in their systems. And here's again some misspelling. And this is also coercible to a microbial ID we created, which is human readable. It's from the kingdom of bacteria. Here the abbreviation of the genus, which is Staphylococcus, and here the abbreviation of aureus, which is the species. And this package is able to understand the even most severely misspelled items you can think of. So we only put this in as a proof of principle. Right? It wouldn't even say it's uncertain or very uncertain, but if you put in this in our package and would want to know the valid taxonomic name, it would understand, because every Z could also be an S or a C, and every TH could be only a T, and 2H could also be 1A, and that's how we correct for a lot of spelling mistakes. And it would still understand that it's about Staphylococcus aureus, albeit with a very low score, which is based on the Liebenstein algorithm. But if you have a code, for example here, of this antibiotic, then you can go to any property you like, because all this reference data is available in our package. So you just load our package, and you try to input something for the name. And here I put in a brand name, which is bold printed here, and it would just throw the official name. And if you want to know the defined daily dose of an ATC code, right, then it would say, well, I know it's about flucloxacillin, and it would give you just this 2 grams that is for DDDs. Our idea was that you can, with the data you have, you can go from any to any. And with bacteria, same thing. So if you have this code, which is coerced from anything, basically, then you can go back to anything as well. And if you want to get the gram stain, it would give you the gram stain, or the film, which is a taxonomic entry. You can do that as well. So again, you go from any to any. So how can you use it? Well, this is part of an example dataset we included in our package, and it's a very regular healthcare dataset, I would say, with a date, age of patient, gender of patient, and here the microorganism, MO, E. coli, and some others. And here are 3 columns with results of specific antibiotics. So these are the results for amoxicillin, for ciprofloxacin, and for trimethoprim. And I would estimate that most of you are treated at least once in their life with any of these 3 antibiotics. They are also very common for treatment of urinary tract infections. R means resistant, so this Klebsiella pneumoniae is resistant to amoxicillin, but it's susceptible to ciprofloxacin and trimethoprim. And here we have missing data, which is also very common, because you won't test on every antibiotic for every bug you run into in a laboratory. So there's, in medical microbiology, a lot of missing data. But with only a couple of lines, I hope you understand a kind of tidy-first syntax. Here we have our example dataset, and we group by this column by hospital data, and then we summarize where we calculate the resistance of amoxicillin, and with n_RSI we counted the number of isolates where there's a valid result, so resistant, susceptible, or intermediate, somewhere in between. So here's the result, and you can see immediately that for hospital A, there's an empiric resistance to amoxicillin of 55.4% based on 157 isolates. But what's more important is to look at susceptibility, because that's the chance of success you have to treat your patients. And you can give amoxicillin alone, and you can give ciprofloxacin to a patient alone. But what's very common, especially in ICUs, that you treat with 2 different antibiotics, because you have to be sure they make the end of the day. And if you don't know what's causing the super severe infection, then you're better safe than sorry and treat with multiple drugs. You can use that in our package. And here you see, again, grouped by hospital, you see here that the susceptibility to amoxicillin is 44.6. Of course, it's 1 minus the 55.4 we saw earlier. And you see also here that ciprofloxacin is way more successful than amoxicillin as a monotherapy. But if you combine the both, you would get a success rate, empirically, of 92.4%. So that's a big difference. So using this package, you can also evaluate treatment and give advice on which drugs would work best in what way, or for which hospital, for which ward. You can group on anything, right? On hematological patients, or patients with respiratory diseases. So if you want to install it, obviously you only need to input a command, or if you are in our studio, just type in AMR and you can use that. We also created a package down website with a lot of how-tos that are included in our package as well as vignettes. And there you can read how this package works and what it all can do and so forth. We also wrote a methods paper about this package and submitted it to bioRxiv as a preprint, and it's currently under review at some journal. So we are curiously awaiting that results. There's a lot of people to thank for the development. We couldn't, of course, do this alone. There's software testers from, I believe, 7 different institutes in also different countries, and it was great to work with all those people. If you want to contact me, please do, and we'll get in touch. Thanks for listening.